Today's topic probably needs no introduction. It's one of the most basic and most powerful tools in engineering, and chances are you've already used it in your own projects more than once. By using its power without really understanding it, that can lead to some shaky results. Ready to finally master the principle powering most of your projects? Stick around and I'll show you how. Today we're diving into the essential theory behind aiming in video games, vectors. We'll learn about what they are, how to work with them, and how to make them do cool stuff in Unity. These are key concepts that are must-have for serious game developers. Just a little heads up, this video requires some background in coordinate systems, which I covered in a past video. If you need a refresher, link is in the description. Vectors are one of the most basic mathematical objects that are defined by two properties, direction and magnitude. For example, velocity is a vector with direction, which tells us where the object is heading towards, and magnitude, which is the object's speed. But what does direction even mean? Direction only makes sense relative to something, like a coordinate system. Take the vector 2 and 3 for example. On its own, that's just a pair of numbers. But in a Cartesian coordinate system, it means 2 units to the right and 3 units up. Now these two numbers have a meaning. They show the direction and magnitude of the vector. We'll explain a little more on these properties throughout the video. Many times in engineering and in game development, we want a property of a body A in relation to a body B. These are described by relative vectors, like relative velocity, acceleration, etc. For example, let's take position, which is also a vector. A player's position is defined by how far it is from an origin, the magnitude, and in one direction. Let's assume that our target is here at Cartesian position 2 and 3, relative to the origin. This vector has x and y components, which in turn tell us how far and in one direction is the target from the origin. Now let's assume that our player is at position 3 and 1 relative to the origin. If we want to find the position of the target relative to the player, we will have to travel in the opposite direction to the player position vector and in the target's direction. This essentially means subtracting the two vectors. If we carry out the calculations, we'll arrive at this vector, which is -1 and 2. That tells us that the target is 1 unit to the left and 2 units up from the player. In our project, our first order of business is going to be creating the aiming method, which is going to take the cursor position and subtract the player position to get the vector from the player to the cursor. However, you may notice that there is a small tweak where I take the normalized version of this direction vector. Without normalization, our projectiles will fly slower when the cursor is closer to the player and faster when it's further away, which is definitely not ideal. So what's going on when we normalize? Let's begin with another example. This time from within Unity. Assume that we want our projectile to move in the direction we calculated inside our aim method, and we want the velocity to be 25. You'll notice that if we simply multiply the calculated direction by 25, the solution will change depending on how far the cursor is from the player. That is because, as I said before, the calculated relative vector also has magnitude in it, which tells us how far the objects are. But the only thing we want from this vector is the direction. So how do we make sure that the aim function gives us only the direction and is independent of the distance between the target and the player? Answer: we normalize the result. A normalized vector has a magnitude of 1. That means that it only has direction. And so now we can multiply it by our desired speed and get a consistent result every time regardless of the size of the vector, because we normalize it to 1 all the time. Under the hood, this is what's happening. Assume that the calculated direction vector is 4 and 3, for example. If we multiply this vector by 25, which is our desired speed, we will get this result. This is how you multiply vectors by a number. You simply multiply each of the components. Pay attention to what this result means. It says that the object's speed in the x direction is 100, and in the y direction it's 75. This certainly accumulates to more than 25. In fact, it accumulates to a total velocity of 125, which is 5 times our desired speed. Remember this result, we'll come back to it later. So, what happens if we normalize? It works something like this. First, we calculate the current vector's magnitude. So for example, if we have the vector of 4 and 3, its magnitude can be calculated by using the Pythagorean theorem, which says that the length of this vector is going to be the square root of 4 squared plus 3 squared, which equals 5. The next step is to take the vector and divide it by its magnitude, so it'll have a magnitude of 1. You see what we're doing there? We're taking the entire vector and we're normalizing by its magnitude, so its magnitude is always 1. This new vector is now called a unit vector, or a normalized vector. These two terms are used interchangeably. The resulting vector is 0.8, 0.6. And if you use the Pythagorean theorem again, you can see that its length is 1. From there, all that's left is to take that unit vector and multiply it by our speed, which is 25 in this example, and get the final velocity vector of 20, 15, which magnitude is, you guessed it, 25. So back in our code, if we want to normalize our result, all we have to do is take our vector and write point normalize, and that is it. It does the entire process for us. Now we have a normalized unit vector, which only tells us the direction that we're aiming at. So all that's left for us to do is to choose a speed for our projectile, instantiate it from the player with a little offset, and send it on its merry way. We do that by creating a script for the projectile and writing a setter method for its velocity. I'll show the process in this little montage. And that's it, we now have a functioning aiming system. That's a wrap on vectors for today. We've covered a very important foundation of game development and showed how it can be used in aiming systems. Try playing around with your own vectors, normalize them, break them, add them, multiply them, have a lot of fun. See what happens. And don't miss out on the episode dropping later this week. We'll make a real-time aiming indicator using everything we've covered and more. So I'll see you then. Cheers, guys!